Okay, I have this keychain. So pretty cool. Darth Maul and Darth Sidious. Pretty great. Yeah, they are really expensive. See, to show that, I'm going to show you. This is my Darth Vader. Can you see that? This is Darth Vader t-shirt. Very good. And then this is not something that you bought at the night market or something. You need to save the tag and show people that this is the real thing. Okay, you need to save this tag. Don't throw the tag away. So this is the real deal. Okay, forget about it. Okay, let's get started. Let us get started. All right, so yesterday we talked about how we can draw this root locus diagram, that you need to embrace this 9-step of drawing the root locus diagram. There's no way around it. And of course, you don't have to memorize this. After doing a few more examples, probably it will come automatically come to you as and when you need it. In our example yesterday, we didn't do this step 8. See, we didn't compute. We didn't go through this step 8, computing the departure angle from complex pole, because all of our poles are real, has only real value. It doesn't have the complex part. So today we're going to look at one example where you're going to have some complex pole. If you have complex pole, then you cannot omit this step 8. Right. So again, we are going to go through this again. Don't worry too much if you don't get this the first time. You're going to have plenty of opportunity today. We're going to do maybe more example today. All right, so let's take a look at example 3.14. So it says, draw the locus diagram for a control system with the open loop transfer function given as below. So you are already given this open loop transfer function. Okay, so you need to extract, if you are given the closed loop system, you need to extract this open loop transfer function from that closed loop system. We are going to use the open loop transfer function to help us draw the root locus diagram for the closed loop system. So we need to go back to our step. Okay, the first one is always to locate the poles and 0 and use X for poles and O for zeros. That's the first step, the first one. Okay, so now here we have 1, 0, and -2, 1, 0, and -2, and we in the denominator of the open loop transfer function. So we have 2 poles, and the poles are complex. This is quadratic equation, and if you compute the roots are a complex conjugate pair at -1 plus 1.7j and -1 -1.7j. So use X for pole and O for 0 and locate that on the complex plane. So we have 1, 0 at -2. So use O for that. See, 1, 0 and -2. Put a small circle around -2 to indicate that is a 0. And then you're going to have 2 poles, 2 complex poles at -1 and 1.7j. And of course, when you have complex pole, it always comes as complex conjugate. So you're going to have another one, mirror image of that with respect to the real axis. You're going to have at -1 minus -1.7j. So here you have two poles and 1, 0. And then on the real axis, see, on the real axis, there is a locus to the left of odd number poles and 0. Now, just pay attention on the real axis only. You only have 1, 1, 0, and there's no pole on the real axis. So there is the first 0, meaning that there's odd number poles and 0. To the left of that, you're going to have locus. You're going to have locus there. And then if you go to step 3, the loci begin at the poles and end at 0 or at infinity. So our locus is going to start from these two poles, and one of them is going to end up in this 0 at -2, and another one is going to end up at infinity. Since we have two poles, we are going to have two locus. The locus will start at these two poles. Somehow, that locus is going to end up is going to finish at a 0 at -2, and one of them is going to finish at infinity. So how is that going to happen? So somehow it's going to leave this complex pole and it's going to enter, it's going to break in into the real axis. And then we can compute that breaking point. Okay, so the loci begin at the pole and at 0 or infinity. Since there are two poles and 1, 0, one of the locus and at 0 at -2, and the other one will go along asymptote along infinity. Okay, so that is step 3. So what is step 4? And then we need to determine the number of asymptote and asymptote line. But here is quite straightforward in this example, because we have two poles and 1, 0. You're going to have just one asymptote line. Okay, so you're going to have just one asymptote line. The number of asymptote is the number of pole minus the number of 0. So we have two poles minus 1, 0. There's only one asymptote line. And you can now compute the asymptote angle at 180. So there's no point of computing the intersection of asymptote because you only have one asymptote and it is at 180. Basically, the asymptote is just to the left of the real axis. Okay, so the asymptote go all the way to the negative infinity on the real axis at 180 degrees. So you determine that the number of asymptote is 1 and the angle is 180. There's no need for you to compute the intersection of asymptote with the real axis. It is located on the real axis, going to the left all the way to infinity because the angle is 180. So that is step 5. Now step 6. Okay, so step 6, so the breakaway from the points of breakaway from or arrival. In this case, we are going to have an arrival point instead of breakaway point. Breakaway is the point where your locus leave or exit the real axis. But in this case, we're going to have our locus enter the real axis. Therefore, we are going to have an arrival point. So we can compute the arrival point the same way we compute the breakaway point by rearranging the characteristic equation for k as a function of s and take the derivative of that, and then you can now solve for the break-in point. So in this case, instead of breakaway point, we are going to determine the arrival, the break-in point. Okay, so you rearrange this is the characteristic equation. Rearrange that solve that for k as a function of s, and you differentiate that and equate that equal to 0. Again, this is a quotient. You can use the quotient rule. v du dx, the derivative of u over v over u, something like that. Please refer back to your engineering mathematics notes. How do you take the derivative of a quotient? It is called a quotient rule or chain rule, something like that. So the v du dx minus something, I can't remember that. So just take the derivative of this quotient. Please refer to your engineering mathematics note, and then you can now solve for S. And then you're going to have two solutions again, 0 and -4. So which one is our breaking point? So we need to look back at our drawing. Okay. So since there's no locus to the right of -2, so we cannot take the first solution. So we need to drop this s equals 0. So s equal -4, we take the s equal -4 because -4 is located on the locus. There's no locus exists to the left of -2, so we need to drop this first solution of 0. So we only maintain at -4. So this is our breakaway, or in this case, it's a break-in point. It is where our locus will enter the real axis. Okay, so and then step 7. Step 7, the loci are symmetrical about real axis, and then they approach the real axis, approach or leaving. Yesterday we have the locus leaving. Today we have the locus approaching the real axis. It will approach the real axis at the breaking point at an angle of plus and minus 90 degrees. So this is the breaking point at -4 that we have computed, and the locus will enter that point at 90 degrees from the top, and then it will enter from the bottom at -90 degrees. So this is where our breaking point, and one of them will go to the right and finish at 0, located at -2, and another one is going to go all the way to infinity. Somehow that branch will come from that pole somehow. So our locus will begin from the pole, and if we leave the pole and somehow enter the real axis at -4. So the next question is, we already know that the locus will start from these two poles, but the direction of the locus leaving this pole, how do we know whether it's going to the right, going to the left, going to the top, going to the bottom, or going at a 45 degrees angle? So you need to compute the departure angle of complex pole. So now we have this complex pole, and in this example, you cannot skip step 8. Okay. Step 8, you need to compute the departure angle from complex pole. Otherwise, you don't know how the locus start. Is it going to the left, directly to the left, or is it going down, or is it going up? So you can compute the departure angle using guideline number 8. So the departure angle from complex pole can be computed. So theta d here is called the departure angle. You compute that by 180 minus angle from all poles, all other poles, plus angle from other zeros. Again, so theta p is angles from other poles. Theta p and theta z are angles from other poles to the pole in question. Okay, for example, if you want to find the departure angle from the first pole here, so you need to compute angle from other pole. You have one other pole and one other zero. And now you can now compute that using the expression that is given in step 8. So let us take a look at the detail. Okay, so since the locus start at a pole, we need to find the direction of the locus leaving the two complex poles. Let us now find the angle that leaving this the first pole at -1 plus 1.7j. So you need to compute angle from other pole. So you have one other pole. So this is theta P1 to that pole in question. So we are finding the angle from other pole to the poles that we want to find the departure angle of. So we have another extra pole there. So this is now our first theta P. We only have one theta P here, since we only have one other pole. So that angle is 90 degrees. And angle from other zeros, we only have one other zero at -2. That angle from that zero to the pole in question. So this is theta Z. We only have one theta Z here. Later on, maybe we'll have more poles and more zeros. Then we have theta P1, theta P2, theta Z1, theta Z2. So in this case, so theta Z, you can compute theta Z is equal to 60 degrees. So let me read this again. So theta P and theta Z are angles from other poles and zero to the pole in question. The pole in question is the pole that we want to find the departure angle of, that pole. And then we have other than that pole, we have one other pole and one other zero. So the angle from the other pole is 90 degrees. The angle from another zero is 60 degrees to the pole in question. And now you can now compute the departure angle using the expression 180 minus 90 plus 60, so you get 160 degrees. So this is the departure angle, the angle that the locus exit the first pole. You don't need to compute the second departure angle from the second pole because the root locus are symmetrical about the real axis. Once you get your first departure angle and the departure angle from the conjugate pair of your complex pole is just the mirror image of that. It is going to be -150 degrees. All you need is just to find one departure angle. Now you can okay, step 9 is not necessary. In this example, step 9 is not necessary because the locus is not going to go to the left of imaginary axis. Our system is stable for all gain. Okay, it is not. So it's going to come up from that pole and going to enter the real axis. There will be no locus to the right of imaginary axis, so there's no need for us to go through step 9. Okay, since we already compute that 150, and then we can now draw. Okay, so the intersection, this is step 9. The intersection of locus with imaginary axis is not necessary since the locus never crosses the imaginary axis. The system is stable for all k. Now we are ready to draw our complete root locus diagram. So this is now the departure angle from the first pole at 180 degrees. So you measure 180 degrees. So this is that is the direction the locus leave the first pole, and somehow it's going to come back at the breaking point at -4. It will enter the real axis at 90-degree angle. And then from the second pole, it is just symmetrical. It is just symmetrical about the real axis. It is just a mirror image about the real axis. So this is your complete root locus diagram. Your locus will start at the pole and end at 0. One of them end at 0, and the other one will go all the way to infinity along the asymptote line. Okay, so there you go. So we have now discussed all 9 steps of root locus, how we can draw the root locus diagram. Do you have any question? If you have any question, then you can ask your question in the chat box. All right, so see how nice is that? It's very, very neat. Oh, okay, let's try one more today. Let's try one more example today. Okay, so let us try one more example. 12, we have done this. 13, we have done that. 14, yeah, this is one that we discussed today. And let's try one more. Okay, now here we go. So draw the root locus diagram. Now we have third order system with 1, 0, and 3 poles. 1 real pole and 1 complex pole. So again, example 315. I guess I have that here. See, my job is easier since I already have all this note written down. But we need always to go back to this 9. So this is our friend. This is not our enemy. There. Here, the root locus procedure 1 to 9 is our friend. They are not our enemy. Believe me, they are our friend. It seems that they are nasty to us, but no, they are our friend. Okay, let's go through the step again. So we are given this open loop transfer function. Okay, so draw the locus diagram for the control system with an open loop transfer function. Most of the time in your exam, you will not be given this open loop transfer function. You will be given the block diagram of a closed loop system. So it is our job to extract this open loop transfer function from the closed loop block diagram, from the system given as the closed loop system in terms of block diagram. It is KGH. K is the controller gain, G is the forward path transfer function, H is the feedback path transfer function. Okay, so our first task is to determine, to locate the poles and 0. So here we have 3 poles, 1 at the origin. Yeah, so I'm avoiding the word 0 because I'm going to reserve zeros for the value of S in the numerator. So we have 3 poles, 1 real pole at the origin, and we're going to have 2 complex poles at -1 plus J and -1 minus J. And we have 1, 0 at -2. All right, so that's it. That's the pole and 0. So how many asymptotes are we going to have? So the number of asymptotes is the number of poles, which is 3, minus the number of 0. So 3 minus 1, we're going to have 2 asymptote lines. When you have 2 asymptote lines, we're going to have to compute 2 asymptote angle. So 2 asymptote angle is computed using R equals 0 and R equals 1. So we're going to get 90 degrees and 270 degrees. Since we have 2 asymptote lines, so it does not make sense to compute the intersection of asymptotes. So just substitute the value of the poles. So summation of pi are the values of the pole, zi are the value of the zeros. Since we only have 1 0, so you have that minus -2 there. So that's 0 minus plus j minus minus j, and then this is, p is the number of poles, z is the number of 0, 3 minus 1. So the intersection of asymptote happens at the origin, equals 0 here. Now you can draw the asymptote line, and then okay, so you have 3 poles and 1 0 at -2. Okay, so the intersection of asymptote is at the origin. So this is the intersection of asymptote exactly at the origin, coincide with the first pole. So the first pole is also at the origin. Intersection of asymptote also in this case coincide with our first pole here. And then our first asymptote line is at 90-degree angle. So 90 degrees is exactly the imaginary axis. So the imaginary axis is our first asymptote line. The second asymptote line is at an angle of 270. So 270 is exactly the negative part of your imaginary axis. So in this case, our locus will not cross over to the right of imaginary axis by the reason that our asymptote line is exactly on the imaginary axis. It will approach the imaginary axis, and then it will approach the negative imaginary axis. Since we have three poles, we are going to have three locus, three loci. One of them will end up at 0 at -2, one of them, and then the other two will approach our asymptote line. And then on the real axis, I'm forgetting about what number of guideline here. See, on second step here, on the real axis, the locus exists to the left of odd number poles and 0. On the real axis alone, so this is the first pole is odd, so there's a 0, that's even. To the left of odd number poles and 0, you're going to have locus. So from origin to -2, you're going to have locus. To the left of -2, there's no locus there. So one of the locus start at the origin, and then it will end up at -2. That's one of them. The other two locus will end up along asymptote. Okay. And then since we have this two complex pole, we need to determine the departure angle. So the departure angle is, we can compute the departure angle using this expression, 180 minus angle from other poles plus angle from other 0. Let's say we want to find the departure angle from our first pole. So we have two other poles. So you need to compute the angle from other pole. So we have theta P1 here, 135, and theta P2 is equal to 90. And then we need to plus angle from other 0. We have one other 0 at -2. So we have a 0 at -2. So that angle is 45 degrees. So this is our theta P1, 135, theta P2, 90, theta Z1 is 45. Substitute that in the expression for departure angle, and then now we have the departure angle happens to be at 0 degrees. 0 degrees meaning that our locus will leave the complex pole exactly to the right. Horizontal to the right is the angle 0 degrees, exactly to the right. And then step 9 is not necessary because we are never going to cross the imaginary axis. Okay, now we are ready to draw our complete root locus diagram. See, there's no breakaway point as well, so you don't need to compute the breakaway point because the locus will not enter the real axis, so we don't need to compute the breaking point as well. So we are ready now to draw the locus diagram. So this is so we start with these three poles and 1, 0, and we know that our locus will start at the pole. One of them from our first pole at the origin is going to go to the left and end up at the 0, end up at 0 at -2. Since we only have 1, 0, the other two locus will end up at infinity. So this is our asymptote line, exactly on the imaginary axis. So the blue line here is the asymptote line. So our locus will never cross to the right of imaginary axis. The departure angle is at 0 degrees, so it will leave our first complex pole horizontal to the right, and then it will turn approaching the asymptote line along this. It will go all the way to infinity along that asymptote line. And then root locus diagrams are symmetrical about the real axis. You don't need to compute the second departure angle. So this also will go to exactly horizontal to the right, and then it will turn down and then approach this asymptote line. So this locus will end all the way to infinity along the second asymptote line. See how neat is that? I'm amazed. I am amazed how beautiful my root locus diagram turned out to be. It's so neat. I can phantom that. I cannot imagine it was going to be this neat. Okay, so do you have any question? Yeah, it is a freehand drawing, except for the axis, of course. I draw using ruler for the axis, and for the straight line, of course, I use ruler, and the rest I use just my free hand. Do you have any question? Okay, so I guess next week is our semester break, right? Yeah, so we don't have classes next week. Yeah, so let us just take a break. And I was thinking of giving you assignment, but no, let's just take a break and forget about classes. Okay, so this is the end for today. There are a few more examples. We're not going to go through that. We'll talk about a few more examples next time. If you have any question, then you can ask the question in the chat box, or you can ask your question verbally. We still have a few more minutes left. All right, so I guess happy holiday. Take a good break. I know we're not going anywhere. I'm just going to drink a lot of coffee in my backyard. May the force be with you too. Thank you, everybody.